So if we want to find a power series for this, then if we change this over to something that we've dealt with before, make it kind of look like geometric series A over 1 minus R, then what would we do? We could say that you could rewrite that as 1 over 1 minus x cubed. Is that right? Minus negative x cubed. And so then that would make your R here equal to a negative x cubed. And remember, the geometric series is a power series is geometric is a times r to the n. Okay, n equals 0 to infinity. So our a here is 1, so that would just be 1 times negative x to the third to the n. And then remember, I told you you could rewrite this. And how could we rewrite that? Negative 1 to the n, and then of course x to the 3 to the n would be x to the 3n, like you just said. Okay, and so that would be the power series representation for 1 over 1 plus x cubed. Now I'm going to introduce a pretty easy to understand concept. If we have something that looks similar to something that we already know, like let's say I wanted to find the power series for f of x equals 2x squared over 1 plus x cubed. And so the previous problem we figured out how to find the power series for 1 over 1 plus x cubed. So we can think about this function like it's 2x squared times 1 over 1 plus x cubed. And then we know the power representation for 1 over 1 plus x cubed. So we simply say 2x squared times, so our power series is two x squared times that power series okay, and then we have a x squared times a x to the 3n. Okay, and we have a 2 that we can write in front of the negative 1 to the n. So this is 2 times negative 1 to the n times x to the, remember, add the powers whenever you multiply same base. So that's the 3n plus 2 power. And so what you might want to do, what if we'd have been given the second problem over the first problem? You know, if I wouldn't have been given the first problem, what you might want to do is try to think about this in terms of splitting up the numerator and denominator into two different functions, and then work with the one that you can change into the geometric power series, and then multiply this back in at the end. So, for example, you know, if we're given one that has multiple parts, say like this, I'm going to give you a minute or so to try to figure out a power series for this. What I would do though is I would think about this like it was x times 1 over 5 minus x. Get the power series, do whatever you have to do to this and manipulate it to get it in the form a over 1 minus r. And then after you have that, then multiply in an x at the end. So if we deal with this fraction, this part of the fraction here, we want that to be a 1. So to make that a 1, you'd have to divide that by 5. Well, then you have to divide that by 5, and you'd have to divide that by 5. Whatever you do to the denominator, you can't just divide the first term by 5 just to do it. I mean, it's like multiplying the denominator times 1/5 and the numerator times 1/5. So now we have this thing here where r is equal to x over 5 and a is equal to 1/5. Okay, so summation here. The formula is a times what? R to the n. And so it's summation 1/5 times x over 5 to the n. And so what I would do now, if you raise the numerator and denominator to the n, then you have, we have 1 over 5 x to the n over 5 to the n. So that's x to the n over 5 to the n plus 1. Okay? And the only thing we have left now, that's for this part. And we have an x here that I brought out so that we could just deal with the geometric part. So just say x times this thing, and we have x to the first and x to the n. So my new power series is going to be x to the what? N plus 1. It's over 5 to the n plus 1. And so by breaking it apart and just working with the geometric part first, it kind of simplifies it a little bit.
So would you write your simplified answer as x to the n plus 1?
Remember what we went over about we could use derivatives to maybe help us write power series. What if I had the function f of x equals natural log of 5 minus x. Now we just dealt with something that was very similar to either the integral or derivative of that. So if I took and found the derivative of the natural log of x of 5 minus x, that would be 1 over 5 minus x times the derivative of 5 minus x, which is negative 1. So negative 1 over 5 minus x is the derivative of the natural log of 5 minus x. So that means that the integral of negative 1 over 5 minus x is equal to the natural log of 5 minus x. And so if we can figure out a power series for 1 over 5 minus x, and we stick a negative in front and take the integral of that, that will give us the power series for natural log of 5 minus x. Okay. And earlier, do you remember this part right here was the part that we dealt with to find the power series first. We made it a geometric power series. And this right here, or if you could put the 5's together and make that just 5 to the n plus 1 in the denominator. So that was summation n equals 0 to infinity of x to the n over 5 to the n plus 1. And so if we just integrate the variable part, this 5 to the n plus 1 is a constant. So if we integrate this part, we add 1 to the power and then divide by the new power, right? So this is going to be the negative could be x to the n plus 1 divided by n plus 1. See, that's where this power, when you integrate, you add 1 to the power and then divide by the new power. Usually though, when we integrate, we put plus c. So I'll put the c there in the front, so we have c minus this here. Okay. So here's what we have. The natural log of 5 minus x is equal to c minus the summation x to the n plus 1 over 5 to the n plus 1 times n plus 1. Now, we could figure out what c was equal to by plugging in any value for x. You learn to do this more in differential equations, but it's real easy to see here that if we plugged in x equals 0, so I'm just going to say for x equals 0, you may say, well, why did you choose 0? Because I can plug in 0, and a lot of times plugging in 0 into equation is the easiest thing to do, so I'm going to plug in 0 for this equation and see what happens. So if I plug in a 0, I'm going to have the natural log of 5, because that would be a 0, equals c minus, again, I'm plugging in a 0 for x, so this is 0 to the n plus 1 power over 5 to the n plus 1 times n plus 1. Alright, and so it doesn't matter what the bottom is equal to. What's the top always going to be equal to? 0. So this will go away, and we solve for c. We find our constant of integration is just the natural log of 5. Okay? And so we can write the power series for the natural log of 5 minus x as, I just solved for c, so it's the natural log of 5 minus this power series n equals 0 to infinity x to the n plus 1 over 5 to the n plus 1 times n plus 1. So if you look back at your notes for the Tailor and Maclaurin polynomial, you'll notice that the formula for the Tailor and Maclaurin power series is the same, or very similar. It's thought of very similarly. For Tailor's and Maclaurin series, we follow the formula summation n equals 0 to infinity of the nth root or the nth derivative evaluated at c over n factorial times x minus c to the n. Alright, and so I can write that out expanded a couple terms. You know, if we let n equal 0, the 0th derivative you think of as just the original function. So the 0th derivative evaluated at c would just be f of c. And then this would be x minus c to the 0, which is 1, over 0 factorial, which is 1. That would be, so the first term of your Tailor or Maclaurin series is just f of c. Plus, then if we plug in a 1 here, it will be the first derivative evaluated at c times x minus c to the first power over 1 factorial. I'll write the 0 factorial and the 1 factorial on the bottom here. But usually they're not written in the formula because, you know, if it's 0 factorial and 1 factorial are just 1. I'll write one more term out for you. So if I plug in a 2, I have the second derivative evaluated at c times x minus c to the second power over 2 factorial. And then we just keep going on and on like that. As many terms as we need, we would keep going on and on like that. And so the reason for writing out the terms is usually so you can figure out the patterns, so then you can go back and write the power series or the Maclaurin series or the Tailors. So this formula, as long if c equals 0, then it's called a what? Then we have a Maclaurin series. If c is not equal to 0, so c is something different, it's called a Tailor series.
Can you have a Maclaurin series then? Because if c is always 0, you can always end up with a 0 over a number.
Of x. A power series for f of x equals sine of x centered at 0. So we're going to need to first write down our function and several derivatives. Yes, sine of x. So if I write down my function, you can see a pattern is formed after I get past the third derivative. The fourth derivative starts over. So the fifth derivative would be the same as the first derivative, and the sixth derivative would be the same as the second derivative, and so on and so forth. Alright, so I'm going to stop there. And now if I'm centered at 0, that means this is a Maclaurin's. So I need to find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and the fourth derivative evaluated at 0. And you'll see a pattern form. F of 0 is 0, f prime of 0 is 1, f double prime of 0 is going to be the negative of sine of 0, which is still 0. Then the negative of cosine of 0, Cosine of 0 is 1, so that's negative 1. And then the pattern starts back over. So 0, 1, 0, negative 1, 0, 1, 0, negative 1, over and over and over forever. Alright, now if we apply the Maclaurin series or the Maclaurin or Tailor formula to that, then I can write out a couple of terms here. Alright, so if I write out, let's say, the first 4 or 5 terms, summation n equals 0 to infinity of, what is it, the nth derivative evaluated at 0 over n factorial x to the n is equal to, what's our first part of our formula? We need f of c divided by 0 factorial. So we were centered at 0, so the first term is just 0 divided by 0 factorial. Plus, the second term, we need f prime of 0, so that's 1, times x minus 0 to the first power over 1 factorial. Alright, plus 0 times x minus 0 to the second power over 2 factorial. The fourth term, we need, if we plug in a 3 right there, we need the third derivative evaluated at 0. So that's going to be minus 1 times x minus 0 to the third over 3 factorial. And so if we wanted to keep on going, we could just keep writing terms, but we need to remember, here's the pattern: 0, 1, 0, negative 1, 0. Like the next term would be 0 times x minus 0 to the fourth over 4 factorial. So that's here, which is the same as this one. Then the next term starts over at 1, so then I have plus 1 times x minus 0 to the fifth over 5 factorial. Then the sixth term would be 0 times x minus 0 to the sixth over 6 factorial. That's a 6. And then the next term, minus 1 times x minus 0 to the 7th over 7 factorial. And this thing just keeps going on and on forever. But you can see, and you really do need about 6 or 7 terms on this one just to get a good picture of what's going on. You can see that, okay, the first term is 0, so that's nothing. Then this one here is going to be 0 times that, so it doesn't matter what any of that is, it's times 0. Then the same here, the same here. So let's simplify the terms. And I'll have 1 times x to the first over 1 factorial is just x. Then I have minus x minus 0 to the third, that's going to be minus x to the third over 3 factorial. My next term here was plus, this will be x to the, I didn't write my factorial down there, x to the fifth over 5 factorial. From that point, you can probably see the pattern. It's positive, negative, positive, and it's going to be negative, positive, negative, positive, negative. You can see that we have odd factorials in the denominator, and we have odd powers of x. And that's the pattern that's formed. And so you could keep going on and writing out more and more terms if you wanted. But we could also figure out a way to write that in series notation. So what's that going to be? Alright, so we want x to the first, x to the third, x to the fifth, x to the seventh. We also want positive, negative, so on and so forth. So we need that negative number generator. Remember that? It's negative 1 to the n would be good because if I started at 0, because that would make that a 1, and then a negative 1, and a 1, and negative 1. And x to the, how do I get 1, 3, 5, 7, 9, so on and so forth?
n plus 2.
Would that, no, 2n plus 1? Because then, if we let that be 0, that will be to the first. Then when that's 1, that would be 3. And when that's 2, that would be 5. Alright. And I want the same thing in the denominator, but I want it to be factorial. So what is it? 2n plus 1 factorial. So this is the generator for the series for sine of x. That is a Maclaurin series of sine of x. Now, if I wanted a, knowing that, if I wanted to find a Maclaurin series for x squared sine of x, then all I would have to do is take the series for sine of x and say it times x squared. So that would be x squared times this and so we have the same base with different powers, we just add the powers. So that would be negative 1 to the n times x to the, what would that be then? 2n plus 3. Okay. We can use that same concept of using the similar series, the one for just sine of x, to find a Maclaurin series for something like this. Say I wanted to find it for sine of 2x. I can go through the long way and do it like I did for sine of x, or I'm not multiplying the thing times 2x. I just have to plug it in for my x. So don't do it right here where you'd multiplied it times x squared. This right here is sine of x. So what I'd have to do is I would have to, it's going to equal sum n equals 0 to infinity, negative 1 to the n, and now plug that 2x in where the x is. So it's going to be 2x to the 2n plus 1 power over 2n plus 1 factorial. Now you could split this thing right here up because it's 2 to the 2n plus 1 power and it's x to the 2n plus 1 power. So it could be written like this. So it's 2 to the 2n plus 1, x to the 2n plus 1. But you could just leave it like it was previously because splitting it up on this one really doesn't do anything. it's not like I have something that'll cancel out if I do that. I don't. So, yeah, this will probably be the most, I guess, the preferred way of leaving it, because splitting it up really does nothing.